So, you must have understood that when I define line integrals, I depend heavily on the concept of parametrization. And this parameter is a real variable, say t between a and b. Once I know this fact, my attempt of writing a line integral further becomes like this. So, if you know the way I have defined line integral, you know that the line integral for a vector field f has been defined as through the parametrization, right, a to b f of c t dot c dash t dt. So, what I have done is I have converted this so called integration of a vector function into integration of a scalar function involving t. So, that is the key idea behind this definition of the line integral. So, parametrization helps me to convert from a vector valued scenario to a scalar valued scenario involving one variable. Now, the question is that can I write this, because all these integral definitions that we have learned has been done through Riemann sums, limit of Riemann sums. We are essentially talking about Riemann integrals in various situations. So, can we have a Riemann sum representation here? Actually, if you look at it, if you look at the definition, maybe I will just do it here. So, here is my a to b and here is a curve which it parametrizes. So, here is my curve C t. So, you do a partition and you know how to do it now, T1, T2, Ti minus 1, Ti, Ti plus 1 and so forth, Tn minus 1. So, there are n plus 1 points giving you n number of intervals. So, take any interval Ti to Ti plus 1, which we will call the ith interval, and choose a point ui Ti to Ti plus 1 or u whatever you want to say, ui and an element here. So, the Riemann sum that you would create in this case, your delta Si arc length is actually Cti plus 1 minus this is your change in the length of change of the arc length as you move from Ti to Ti plus 1. These are delta Si. So, the Riemann sum, okay. So, the Riemann sum actually, so in this case our Riemann sum, let us write down the Riemann sum here. So, you choose any ui which is arbitrary. So, the Riemann sum would be f of Cui into dot product of delta Si is a vector. So, these are all vectors. So, what we are doing, we are writing individual Riemann sums basically. This is dot SI is CTI minus this C is a vector. So, we are writing for a given partition point, we are writing this as a dot product, because here multiplication means dot product. So, here, so this is written as f of CUI into C Ti plus 1 minus Cti, that is what I write. So, now what I do to get the Riemann sum, I need to sum this whole thing from I equal to 0 to I equal to n minus 1. I need to sum up. So, this is the Riemann sum. Now, the delta SI, now if I write down in terms of the Taylor series, right, C dash Ti, if I write down the Taylor series, linear approximation of it, is delta Ti, which is Ti plus 1 minus Ti plus some error. That is what will be what a first order Taylor's expansion will give me. Please understand, Ti is a real variable. You can say okay, the function is R3, but what we are doing for each component of CTI, CTI plus 1 or CTI, this has 3 components, C1 Ti plus 1 minus C1 Ti, C2, C3, there are 3 components. What are the 3 components? The x, y, z basically. So, on the x part I am applying the Riemann, the Taylor's expansion first order, y part I am writing the Taylor's expansion, z part I am writing the Taylor's expansion and putting them as a vector. So, what I am doing here is like this. So, your C T is expressed as, I am just writing in terms of row vector x t, y t, z t, points on the curve. So, C Ti plus 1 minus C Ti is a vector which is given as x Ti plus 1 minus x Ti, y Ti plus 1, now these are functions from R to R, y Ti, z Ti plus 1 minus z Ti. So, what you will do, you will write here the first order Taylor's expansion, that is x dash Ti into delta Ti plus error, which I am writing as E1. Here what I will do, I will write y dash Ti into delta Ti plus error E2 plus z dash Ti delta Ti plus error E3. So, that is what I am going to write. So, if you take them up, so it will, what will happen? You will have x dash Ti into delta Ti, right, the vector y dash Ti into delta Ti and z dash Ti into delta Ti, that is added with this vector E1, E2, E3, the errors. Now, if I take the delta Ti outside, scalar multiplication of vector, this is nothing but x dash Ti, y dash Ti, z dash Ti plus error, plus the error vector, So, what is this? What is x dash Ti plus z dash Ti plus this damn thing, sorry, this thing is nothing but C dash Ti. This thing is nothing but C dash Ti. Sorry for the use of the word damn, it comes out of excitement, it is no hard feeling to anyone. So, here what you have done, you have expressed this difference in terms of the derivative of C dash Ti. That is why the derivative actually appears in the first place. Now, if the error is very small, delta Ti is very small, then you can write delta Si, you can approximate as C dash of Ti delta Ti. So, in that case, the Riemann sum can be approximately written as I equal to 0 to n minus 1 f of Cui dot C dash Ti into delta Ti. Now, as the whole thing goes to 0, you can understand this is now as limit as n tends to infinity, as n tends to infinity, if this limit exists, if the limit exists, then limit n tends to infinity, you can easily now figure out what will happen. This will become dt, this will become C dash t, this will become f of Ct, because these things are Ti and Ti plus 1 are coming closer and closer as n goes to infinity. So, this limit, if it exists, is marked by the integral where t is varying from a to b, f of Ct dot C dash t del dt. That's the game, right. So, it has a expression through Riemann integral. There are few technical things we should remember about this thing, is that when you are taking a line integral, suppose you have a point A in space. So, let me have a path A, have a point A and a point B in space. So, there is a, I say that I move between A to B along a path C. Then the set that the path C actually determines how you are moving, either you are moving from one A to B or you are moving from B to A. The nature of C will determine that. There is a beautiful example in the book, and the value of the line integral can change depending on which way you have moved, that whether you have gone along C from A to B or whether you have come from B to A, that orientation, that change of direction can change the value of the line integral. So, there is a nice example and which I think is very useful. So, here they give you 2 points in 3 dimension, x is 0 0 0, some point x naught, another x1 point which is the final point is 1 0 0. So, if I draw the axis, so this is my x axis, this is the z axis and this is the y axis. So, essentially I am looking to move from this point to this point along. So, here is the line segment. So, let me remove this line segment and oh my god, maybe I should take the black and join the line segments. The remaining part can be in this color. Which color I have taken? Oh my god. this is making no sense. So, okay. So, now I will describe two paths. One path will take me from 0 0 0 to 1 0 0, another path will take me from 1 0 0 to 0 0 0, and on these two different paths the value of the line integral would be different. Let me consider the vector field f given as I. So, it is 1 into I, it is constant, that f position is always constant, and there are two curves, one is C1t which is t 0 0. So, when it is 0 0 0, when t is 0, it is t is between t is when t is 0, we are at when C1 0 is 0 0 0, when t is 1, that is C1 1, we are at 1 0 0. So, C1 comes along this direction, and then I define another path C2, parameterized path C2. So, this is my curve C1 and this is my curve path parameterized by C2, 1 minus t 0 0 0, small tweaking you see. So, when I put t equal to 0, it is giving me this point, when I put t equal to 1, it is giving me 0. So, there is another path C2 is taking me from this point to this point, the reverse. C2 is taking me on the reverse direction. So, let us now calculate the line integral. So, line integral I will not calculate, I will ask you to calculate, take it as a homework and calculate. The line integral calculation is very, f is fixed here, it does not matter whatever Ct put, it is the value is the vectorial component is just 1, and C dash t is, you know how to what to do, it is a 1 0 0, and of course it is not a very big idea, a very big thing to do, and C dash 1 t is nothing but the I vector plus 0 j vector 0 k vector, right. So, you know how to do the thing. So, it is I dot I basically. So, it is 1 in essentially 0 to 1 dt. So, if I go by the curve C1, so let me call this as C1, the big curve. C1 is this big curve C1 is parameterized by this, the another big curve C2 is parameterized by this. Both are the line segments, nothing more. So, by C1, if I take my line integral, that value is plus 1, but I come by C2, minus. So, there is a physical meaning to this, is F is a force acting on the particle moving along this path. Then if the particle goes from 0 to 1 1 0 and comes back from 1 1 0 to 0 0 0 along C2, then the total work done by the particle is 0. So, you see this orientation has a important thing to do about the value of the line integral. So, this is something that one needs to keep in mind while talking about line integrals. Another thing I do not want to get into, the issue is of reparameterization. I do not want to confuse you at the moment with reparameterization. That is, I can take another parameter u and write t as a function of u, and I change the parameterization of the curve again, but ultimately the line integral values would be same. That is what I just want to tell you. I do not want to get into the technicalities of reparameterization. But now, for example, we are going to talk about the physical aspect of this line integral. We will talk about the meaning of work done. Of course, there are certain things which you need to learn yourself, which is, for example, if you have from point A to point B, if I move in curves A to C and then from C2b, and I call this curve as C1 and I call this curve as C2, then the integral over the whole curve can be done separately, first over C1 and then over C2. I am not writing the vector sign when I am writing it is just as a function on the integral, but it is actually a vector valued function plus C2. So, these are some things you can understand, your intuition is absolutely fine, young people, to understand this. Even if there are some senior people who are watching this, this is not a very big issue. So, we will now talk about physical aspects of this notion of a line integral. One of the most fundamental physical aspect is that of work. Work has already been defined in physics as force into distance. So, work done, so if there is a say a stone lying here and you are pushing it with a force F in this direction and it starts from this position, I am just taking the position of the center of mass and starts from a position x1 and reaches a position x2 along the real line, right. Then the work done is simply the magnitude of the force into the distance that is travelled, that is work done. But when you come to higher dimensions, when an object, a particle is moving in a trajectory, then there this distance, how will you compute the distance? The distance is a vector, the distance has to be given by a vector, and of course, the work done has to be expressed in terms of a scalar product. Work done cannot be. So, basically what you are doing, you are looking at the work done along all the components and then summing them up, and that is exactly the inner product. So, basically if there is a particle here in 3 space and here is a force acting on it, and this force can be decomposed into 3 component forces. I am just talking about mechanics now. Those who know some mechanics will understand. This is F1, F2, F3, and that is why these are the component forces, right. So, that is why this F vector, F is viewed as a function from R3 to R3. So, there are 3 components, because you can decompose a force theta, if there is a particle and a force is acting on it, I can decompose it along the horizontal direction, the what I call horizontal direction, the vertical, the height direction, along the length, along the breadth, along the height, 3 directions. So, now when you have decomposed it, now you assume that you are making a small movement along. So, if you take a particle and if you move it along a very small movement, you make a very small movement from here to here. This is a displacement vector, which is dr vector, can be expressed into 3 different components one along the length, breadth and the height, that is dx, dy and dz. You can decompose it along these 3 directions. So, then along the direction of x, the work done is F1 into dx. Along the direction of y, the work done is F2 into dy, and along the direction of z, the work done is F3 into dz, because we are doing components are decomposed along length, breadth and height. So, the force acting along the x direction is F1, so F1 into dx along sorry, I have to make it F2 here, sorry, this should be F2 just to maintain a symbolical things. And along the breadth y direction it is F2 and along the z direction it is F3. So, then the magnitude work is a scalar, you have to give the magnitude of the work, you do not talk about work direction of work, it is the magnitude how much work you have done. Energy is the capacity of doing work in some sense. So, work, so because when you do work you expend some energy. So, F1 dx is the work along the x direction, F2 dy is the magnitude of the work along the y direction, F3 dy is the dz is the magnitude of the work along the z direction. So, total magnitude of the work is this along in this small once you make this very small movement, this is the total magnitude of the work. And so, if you move along a curve C, this is the total work. So, this one dimensional idea is again brought into the higher dimension and you know what is this, this is the differential form and you know how to do this thing. This is not the only case, this is not the only scenario where this is not the only scenario where this line integral can be used. Let me talk about the notion of work done in a gravitational field, right. So, suppose there is a 3-dimensional particle and at every point other than the point origin 0 0 0 0 the gravitational force field can be defined and that we know how we can define it. So, the gravitational force field is defined in this way. So, how is the gravitational force field defined? You know the gravitational force field F is an attractive force. So, if a bigger mass m is there and a smaller mass m gets attracted, right. Now, I will put this bigger mass at the point 0 0 0 or it does not matter, I will put it at some point say x0, y0, z0 and the smaller mass at the point x, y, z and x, y, z is not equal to 0. Then along this line there is a force which attracts m towards capital M, this mass. So, this is an attractive force and it is along the direction negative to the radius vector by which I reference the small m with respect to the capital M. So, the gravitational force is always written like this, if this is r for example, if this was 0 0 0 then it is g m by r vector, the distance between them r cube into r vector with a minus sign because this minus sign is telling that this force is attractive. Now, what happens is that here if I write it down then I can write at any point x, y, z where a particle of mass m is there, I will write it down, I will take this x0, y0, z0 as 0, the bigger mass is at the origin, this is the origin, that is this is the point 0 0 0 and at any other x, y, z not equal to 0 0 0 the mass, the whole thing is written as g m m by r cube. So, basically r is root over x square plus y square plus z square cube of that into the r vector. And what is r vector? X vector, xi vector plus yj vector plus zk vector, right. And this can be written as minus g m m into x square plus y square plus z square to the power 3 by 2 into r vector is xi vector, yj vector and zk vector. This completely defines the vector field f. If you want, I will put a f symbolism here. It completely defined, its components are. So, if you want to write it as a function from R3 to R3, then this is given as, I am writing as a row vector instead of a column vector for just for the convenience of the space. It is written as g m m x square plus y square plus z square to the power 3 by 2 into x minus these are the functions, this is your f1, capital F1, g m m by x square plus y square plus z square to the power 3 by 2 y minus g m m by x square plus y square plus z square to the power 3 by 2 into z. That is the way I write it. Now, let me look at, so let R1 vector be given by a point x1, y1 and z1. So, I am moving the mass in a gravitational field from x1, y1, z1 to x2, y2, z2 and R2. So, here is a big mass and here is first position and then is the second position. So, R1 is this and R2 is x2, y2, z2. Then I really have to find the work done by the gravitational force field, work done by the force F. To move from R1 to R2, to move the particle from R1 to R2. It is like a sun and the planet is moving. So, there is always an inverse square law of force, the gravitational force towards the sun, because when the earth is moving around the sun, the earth is constantly be pulled towards the sun by the earth's gravity, by the sun's gravitational force field. Okay. Now, how do I calculate this? It is very important to understand that the gravitational field is a gradient field, F is a gradient field. That is, grad f itself is a gradient of some function f. So, what is that function f? So, f is actually g m m by r. F is actually g m m by r. Now, the work done by the gravitational field to move from this point to that point is same as grad f dot s ds, and that is nothing because for a gradient field we just it just depends on the value of the function f at the 2 points. So, it is f of x1 or r1 if you want to say, f of r1 minus f of r2, sorry, f of r2 to r1. So, it went from r1 to r2, this is. So, what is that? So, the work done finally is g m m into 1 by r2 minus 1 by r1. So, it just depends on the radius vectors, value of the radius vectors, that is all. So, f is the scalar field whose gradient is the vector field. So, the negative of f, if I write the negative of f as v, then v is called the gravitational, by definition, by convention we do it. It is not that we really have to do it always, but it helps in many calculation. It is called the gravitational potential. So, you see how this basic idea of line integrals can be helpful even in determining how a particle moves in a gravitational field and what is the work done on it. So, we are learning some mechanics, and mechanics is always fun. So, with this I close this talk, and in the next one we will talk about surfaces. So, if you can parameterize a curve by a single variable, can a surface be parameterized? I may not know whether it is a graph of any function, but if I have a surface, can I parameterize it by 2 variables, 2 real numbers? The answer is yes, and that is what we will discuss in the next class. So, thank you once again.